So now we're going to look at some oscillations with mass and springs. A type of cuckoo clock keeps time by having a mass bouncing on a spring, usually something like a cherub in a chair. What force constant is needed to produce a period of 0.5 seconds? So what we're always going to be using, the equations that they give you on the AP Physics exam is the period is equal to 2 pi root m over k. And you're just going to be rearranging this. So I need a k, so I can solve for k by doing t divided by 2 pi is equal to root m over k. So then I could square both sides to get rid of the square root. And then k is just m over t over 2 pi squared. And so in this case, that would be 0.015 kilograms divided by the period, which is 0.5 seconds, divided by 2 pi squared. And all these units look good. .37 newtons per meter. Okay. A spring constant of a simple harmonic oscillator is doubled. By what factor will the mass of the system need to change in order for the frequency of motion to remain the same? So T is 2 pi root m over k. Basically, same frequency if you want to look at it, frequency is 1 over period. So if the frequency is the same, the period is the same. And so if I double the mass of the system, the k is going to have to double also in order to compensate. In order to keep this whole thing constant, if this is twice as much, this is to be twice as much to keep it constant. A 0.5 kilogram mass suspended from a spring oscillates with a period. So the period is 1.5 seconds. The mass is 0.5 kilograms. How much mass must be added to make the change period equal to 2 seconds? So first we're going to say, well, what do I know? T is equal to 2 pi root m over k. I can certainly calculate the spring constant from this. So the most direct method is to figure out what the spring constant is, because I know T and I know M. So if I T over 2 pi, I square it, it's equal to M over K. And so K is equal to M over T over 2 pi squared. And so I can solve for this. Okay. The mass is 0.5. The period is 1.5. I'm going to square that. I get 8.77 newtons per meter. And now I want to make the period equal to 2 seconds. What does the mass need to be? So then I'm going to rearrange this equation and solve for m. M is equal to k times t over 2 pi squared. So that's equal to 8.77. The period is 2 seconds now over 2 pi squared. That's 8.77 times 2 divided by 2 pi. I get 0.889 kilograms. Okay. The other way you could have done this is by ratio. You're going to say, well, the period needs to change. The ratio of the periods is 2 seconds to 1.5 seconds, right? So that's 2 divided by 1.5, and that's 1.33 is the ratio. And if I want to increase this by a factor of 1.33, I need to increase m by 1.33 squared. Because I take the square root of 1.33 squared, I get 1.33. So the mass, the other way you could have done this as a more quicker way, is I could have multiplied this by 1.33 squared, and you'll find that 0.5 times 1.3333, it's 3 repeating, is 0.888 repeating, 9, okay, kilograms. So that's the other way you could have approached that problem. Okay, it's a little small. Suppose you attach an object with mass m to a vertical spring originally at rest and let it bounce up and down. You release the object from rest at the spring's original rest length. There was just there. So I'm attaching this spring, and and right now we're in equilibrium, so the delta x is 0 in this case. Okay, and then I attach the mass here. Show that the spring exerts an upward force of 2 mg on the object at its lowest point. Okay, so what we do in a problem like this when we're doing oscillations, we're saying, well, we have potential energy, and that's going to get converted into, so what's going to happen is this thing's going to bounce up and down. So this is the lowest point, let's say. Okay, and I want to compare the energies between these 2 points. So right here, because delta x is 0 at this point, the spring energy is equal to 0 here, but it does have some potential energy if I assume the lowest point is h equals 0. So it has some potential energy. And down here, it has no potential energy because I say whatever that point is, I'm just saying it's h equals 0, but it has only spring energy. And so in simple harmonic motion, the energy is constant. So whatever potential energy it has up here must equal the spring energy. Or in other words, up here it has mgh has to equal 1/2 kh squared, or k delta x squared, right? Yeah. So these the h's, one of these h's will cancel, and I can solve for I can solve for h, and I'll show you why that's useful. Because if I know h, then I can know the spring force, right, using Hooke's law. So I need to know what k times h is. The force is equal to k times h. So in this case, k times h is my force, so I just multiply this by 2. So I have 2 mg, which is equal to kh. And that's equal to my spring force, because that means I've displaced h, so the restoring force of the spring is going to be here. And so that's that. B, if the spring has a force constant of 10 newtons per meter, or spring constant, and a 0.25 kilogram is set into motion described, find the amplitude of the oscillations. So I think by amplitude they mean want to know what the highest. Well, the amplitude of the oscillation is always relative to 0. So like it would be h over 2 in this case, and if I use this equation, I would have h is equal to 2 mg over k, and so 1/2 h, which is my amplitude, which would be dividing this by 2, is mg over k, right? And m is 0.25. 9.8 divided by 10. .245 meters is the amplitude. That means that's what it's displacing from this point here, the center point of the oscillation. That's the amplitude. Because remember, the amplitude is kind of like a cosine wave. It's always relative to this position. This is my amplitude. It's not the top to the bottom. It's just from the equilibrium position. And find the maximum velocity. So the maximum velocity is when all of the energy is when we're going through the equilibrium position here. Okay, and so the energy at the equilibrium position is I have some spring energy, some potential energy, and some kinetic energy. Okay, so what I have to do is I have to this energy has some potential energy, some spring energy, and some kinetic energy. So the energy at that point is equal to at the equilibrium point is equal to mgh, which is h over 2 in this case, right? Plus 1/2 mv squared, the kinetic energy, plus the spring energy, which is 1/2 k, and it's displaced h over 2 squared. Okay. Now I know what h is. H over 2 is what we got here, is 0.245. So this is, I can then set this equal to, doesn't matter, I could say mgh, the potential energy at the top, or yeah, mgh, okay. So actually what I can do is, I need to solve for mv squared, so I need to bring all of this to the other side. So I have 1/2 mv squared plus is equal to mgh minus mg h over 2 minus 1/2 k h over 2 squared. Okay, and I can compute this whole quantity and then divide this by 1/2 m to get v squared, and then take the square root of that to get rid of squared. Okay, so I'm going to do square root of mgh, so m is 0.25 times 9.8 times h, which is, just to have h is equal to 2 times this, Actually, I need, if I subtract it, I just get h over 2. But just to be clear, h is 0.49 meters. Yeah. Times 0.5 minus 0.5 times 10 times divided by 0.5 times 0.25 and square root of that. I get 2.76 meters per second.
Thanks for watching. If you enjoyed this video, I go through a lot more of these exact kinds of problems with much longer videos on my website. It's entirely free. Check out the link in the description below.